Welcome to myprojectbuzzer.com. Here we discuss about power-up sequence control for MTCMOS designs. Reducing power consumption has become very important in recent years due to the increase in transistor density and clock frequency as well as consumer trends in high-performance portable and embedded applications. Dynamic power losses are sufficient but can be mitigated by techniques such as clock gating, which reduces the power consumption of ideal sections of synchronous circuits. Asynchronous designs offers these advantages inherently as they are data-driven and are only active while performing useful work. In other words, asynchronous circuits implement the equivalent of a fine-grained clock gating network. However, while dynamic power loss has been dominant culprit in the past, static power loss has become a considerable contributor to power consumption in nanotechnology. One of the main causes of static power loss are leakage currents. There are a wide array of techniques designed to reduce leakage currents. The most effective techniques involve power gating circuits, essentially cutting off the pull-up network and pull-down network from one or both power rails during idle or sleep periods. During active period, the circuit is reconnected to the power rails in a process known as wake-up or power-up. While power gating has been adopted for use on asynchronous circuits, most of these efforts involved direct applications of synchronous techniques to asynchronous system. As such, the unique capabilities of asynchronous circuits have not been fully leveraged in the context of power gating. Many asynchronous circuit families are robust to the wide range of supply voltages, ambient temperature and power variations. We exploit this robustness in the context of power gating to enable a zero delay wake-up scheme for pipelined computation. The first token traveling through a pipeline turns on downstream pipelines, hiding the latency cost of wake-up in the computation time of upstream pipeline stages. Synchronous circuits cannot take full advantages of such aggressive power gating control scheme, as local supply power voltages must reach nominal values to prevent the synchronous circuit from violating its timing requirements. Example, setup or hold constraints of state holding elements. Therefore, inputs can only be applied to a pipeline stage once the supply voltage has reached an acceptable threshold. By leveraging the supply voltage operating range of asynchronous circuits, we can avoid these requirements and begin useful computation before the supply voltage has stabilized, reducing the forward latency seen by the first input token. Now I am going to explain the flow diagram of our project. In the first stage, we provide the CMOS switching devices as like in multi-threshold CMOS device. Here, it will be combined as a group power switches because each and every CMOS switching will gets the multi-threshold ranges of with high-speed switching capabilities. For each and every switching bank circuit, this will be generated for different types of delay purposes in nanosecond ranges. Then this was split in overlap switches. This is the overlap switches will generate the bank switching circuits for either micro and macro devices which are arrangement in rows and columns as in the group. Normally, these switching devices will be made to combine the banking circuits of the RAM or any other memory devices to get the switching capabilities to provide the range. Then finally, from the macro groups and sets the columns of based groups. This will provides the transformations connections. The transformations connections provide the internal connections of each and every switching banks. This will make the two steps of internal connections. Either this may made synchronous or asynchronous basic connections. Then finally, we utilize the switching groups and provides the switching effects with different delay performance. For each and every switching devices, we provide the different types of delay performance range and gives the frequency input as an input to trigger the switching devices on state or off state. Here, this will be combined in any other switching circuit which or may be applicable to usage of to provide the delay performance. Now I am going to describe the running procedure of our project. Here, the circuit displays the total overall MTCMOS basic switching bank circuit. For each and every base connections, this will be connected to separately given time allocations for to perform the delay performance. Here I separated each and every bank circuits as in 10 nanoseconds differences. For each and every 10 nanosecond differences, these bank circuits will be interchanged their switching devices, and finally this will be provided as an output waveform structure. Now we simulate this option by click the setup simulation and select the transient or Fourier analysis to choose the timing limitations of our output waveform providence. Here I choose the 100 nanoseconds and 10 nanoseconds for step size. Then click the run options to provide the running operation and extract the waveform structure of our proposed work. This will display the switching bank circuits and the delay levels of each and every switching stage, and finally we extract the waveform structure of our proposed work of MTCMOS structure. This is our running procedure of our project. Thus we extract and minimize the leakage levels of switching circuit by using MTCMOS architecture. Thank you.